Well, welcome to today's lesson on finding extrema or extreme values on a graph or extreme values of a function. So those are values that are either going to contain the highest value or lowest value ever on a function. So we'll start with a little bit of vocabulary here. You might want to print this out so you can see it better and follow along that way. So for now, we're going to look at this graph, and we're being asked to put a star at all local or relative maximums. So right here, I would see that there is a local maximum because that is the highest spot in that particular region. I would also put another star here. That's another local maximum, and then here as well. This would be a local maximum. Then we're supposed to circle the star that is showing the absolute maximum. In other words, which one of these would have the highest y value? It would be that one right there. Then we're going to put a square at all local or relative minimums. So here would be a local minimum, and here as well would be another local minimum. Now we're asked to indicate the slope of the tangent line at each one of those symbols. So right here we would say the slope is 0, so you can picture a tangent line being straight there. Here, the tangent line would have a slope that is undefined. This is called a corner. So the slope coming in from the left would be maybe -1. The slope after that point to the right would maybe be +1. And that is called an abrupt change. That is called a corner. So right here, you would say the slope is undefined. Over here, if you pictured a tangent line right there, you would say the slope is 0. Right here, you would say the slope is 0. And again here, if you were picturing a tangent line getting closer and closer from the left, it looks like the tangent would have to be vertical, or coming in from the right, it looks like the tangent would be vertical, so the slope of a vertical line as well would be undefined. So we're going to be referring to the maximum or minimum values of a function. So those would be called the extreme values, or they could be called the extrema of a function. So to be a local one, you just, that value of the function, in other words, the value is always referring to the y value of the function must be greater or less in case of a minimum than any other y value nearby. Whereas the absolute or maybe global maximum or minimum must be the highest or the lowest value ever on an entire graph. So if you have, let's say, a graph, a polynomial graph of odd degree, where the range is the fact that y can be any real number, you'll never have an absolute max or min because that graph would continue forever up and down. One thing we do know though, at that extremum value, the slope will either be 0 or it would be undefined. So if I'm at a highest value ever, let's say this on a parabola, I know my tangent line there would have a slope of 0, or this way, if it's the absolute minimum, my slope is 0. Or in a case of an absolute value or a cusp, this is definitely a local min, this is a local min, but the slopes there would be undefined. Okay, but the function has to exist, so the function itself, so slope we're talking f prime, function we're talking f, the actual function must be there, must be continuous, must be defined. Okay, so an x value which makes the slope equal to 0 or the slope undefined is called a critical number. So we'll be using that word a lot. So critical number, usually abbreviated by CN, and it's possible for a function to have more than one max or min, right? Local max or min, so a function could have then more than one critical number. So this x value, so the critical number, we're talking about an x value, okay? It will correspond to a point on the original graph. So if you're looking for the full coordinates of that point, you can find the y coordinate by substituting the critical number, so remember that's an x value, into the original equation. Now, depending on the textbook, there's other terminology. Maybe that special point or that critical number, maybe they call it a critical point. In some older textbooks, you might also see it being called a stationary point. but there's something very special on the graph that happens at a critical value of x. Now, the fact that you have determined from the first derivative equation that you have a critical number, that's great. Something is going on there. But just knowing that x is 3 is a critical number would not be enough to know what exactly is happening there. Maybe your graph has a maximum right there. Maybe your graph has a minimum right there. Or perhaps a point of inflection. So there's some special characteristic happening at the graph at that spot. Okay, so next page. Here are some examples of functions where they're telling you the critical number is x equals 2. So these have their own equations, and then they would have their own equations for their derivative as well. So from the derivative, something was happening when x equals 2. So if I look here, at x equals 2, if this is the original graph, what do I see happening here? I see there's a minimum. Maybe it's a local, maybe it's an absolute value. Absolute minimum. What could I say, let's say, about the slope there? I can see that the slope at that point would be 0. So at a minimum, I see my slope, in this case, was 0. So over here, at 2, what's happening? That would be a maximum. Okay, so what would the slope here be at 2? Well, that slope would be undefined. Right, vertical tangent lines right there at 2. Okay, right here, something's happening. What's happening? That's not a max, that's not a min, but the graph went from, on this side, it is concave down, on this side, it's concave up, so that is one of your points of inflection. So what would the slope be right there? Kind of looks like 0. Maybe it's a positive value, but it would be very small. I'm going to estimate that the slope right there is 0. Okay, at 2, what's happening here? Now I have a maximum and a slope of a tangent line right there at 2. That slope would be 0. And then over to the right, at 2, what's happening? Well, it went from concave down to concave up. So here's a point of inflection happening, but the slope right there would be undefined. So they all had something going on at x equals 2. The slopes weren't the same, and the actual characteristic that was happening at x equals 2 was not the same. So we really want to be able to find those maximums and minimums. So we have something called the first derivative test. So if you now have found a critical number. So a critical number comes from the first derivative. So you will have found the equation for y prime. You will have factored it. And there's some special number there, or more than one number, that's called the critical number. If we have a certain value, so the the derivative, or the slope of the graph, changes from positive to negative at this critical number. So C is our critical number. So here it was 2. So if the slope changed from positive to negative at that critical number, then you would say that the original function f has a local maximum at that critical number, or at that C. And we can see that happened right here, right? My slope was positive, and then my slope of the graph was negative. So what happens when you go from positive to negative slope? Think about that. I mean, just think about that picture. From positive, then there's a critical number on the x-axis called C. Then I go to a negative slope. Makes sense that I must be at a local maximum. However, if the slope went from negative to positive, so falling to rising, just picture that, falling to rising at a certain value called C, then I would say that the function itself has a local minimum at C. So a graph with a negative slope, there you go. And then all of a sudden it changes to a positive slope. What must be there? That's got to be a minimum. Now, what happens if the slope doesn't change? So it was negative and it still stayed negative, or it was positive and it still stayed positive, but something happened there. That must be a point of inflection. So it does not go in a different direction. So how could that be? Heading up, pause for a minute, still heading up. Look at that. It went from concave down to concave up. Or same thing, I'm heading down and then, heading down all the way, but briefly paused here for a minute. So what happened here? It changed from being concave up to concave down. So these would be critical numbers. They would be x values where something different happened about the graph. So kind of made this into a 4-step procedure that you can follow in terms of if all you're being asked, not to right now, not to draw the graph, simply to find where does this graph have its highest and lowest points, then these 4 steps will get you there. First of all, you will do some algebra. You'll find the derivative f prime. You will set it equal to 0. So here comes your factoring. Then you'll find the solutions, right, through factoring, or x values that make that first derivative, so that equation you now have, equal to 0, or maybe make it undefined. How do we have functions being undefined? The easiest way is for, the slope, but an equation to be undefined would be for the denominator to be 0. So I am now looking for everywhere in this equation I have for f prime. I will look at the top and see what would make the top 0, or I could look at its bottom or denominator and look at what that would make the first derivative 0, and therefore that slope or first derivative undefined. So you're looking everywhere in this equation for f prime, numerators and denominators. So those numbers were so special. There we go, those are our critical numbers. So anything that either made that equation for first derivative 0, so you're looking in the numerator, or undefined, so you're looking in the denominator. Then you're going to make a sign chart using all the different parts of f prime, so all the different factors. The intervals that will be at the top of your sign chart are going to come from those critical numbers. And then the extrema, or the extrema just means the maxes or the mins, because that's what you're being asked to find. That's why you would want to do this first derivative test, which simply says, again, if you're going from positive to negative, that must be a max right there. If the slope is negative to positive, that must be a min right there. That, in a nutshell, is the first derivative test. Okay, so our job is now to find the extrema, the maxes and the mins, and that's going to be done by using slope. Slope is the first derivative, so that's why it's called the first derivative test. I'm going to find where my slope goes from positive to negative, that would be a max. Or slope goes negative to positive, that would be a min. And then you'll answer the question. So do remember, by the end of this unit, your ultimate goal is to sketch a graph. So don't forget all your Math 30-1 information, your degree if it's a polynomial, your x and y intercepts, your asymptotes, the vertical, horizontal, slant, your domain, your direction, your odd or even, your limits, anything at all, okay? All those things are going to help you. So as we go through this, remember, all you're being asked to do is find the extrema. I'm still going to include graphs. At this point, you wouldn't be asked to do graphs, but it'll help just solidify what we've done at the end so you can see how it all comes together. So the graph at this point is optional. What we're looking for is finding the maxes and the mins. So here's a function, so certain things about it. Before you even continue, what do you know about it from Math 30? Well, you could factor out an x. So for sure, factor out your x, you'll be left with x squared plus 6x plus 9. You continue factoring, and you will end up with this. So there's your x-intercepts, right? You've got 0 and you've got -3. So this is optional, but it's useful material. What's your y-intercept? It would have been the constant in your original function because it came from making all the x's 0. It's just 0. Your asymptotes, well, there's no denominator, so there's no vertical asymptote. And your degree on the top of this function is always larger than the degree on the bottom. So in terms of a horizontal asymptote, there is none. And to be a slant asymptote, the top would have had to have been 1 degree higher than the bottom, so there isn't any. The fact that my leading coefficient is positive, I know this thing is going to head up to the right. Sorry, it's going to head up as I go to the right. So that doesn't hurt when it comes time to eventually drawing the graph. But how are we going to find the extrema? So finding the extrema, we're going to find the derivative, first derivative of this. So we have 3x squared plus 12x plus 9. You can factor out, so we are trying to find the critical numbers. So this is going to be set to 0. We can take out a 3. So now we're left with this. And then we can factor. That would be x plus 1, x plus 3. So your zeros or your solutions of this are your critical numbers. So there's -3 and there's -1. So because there was no denominator in here, these values, if we subbed them back in, make this equal 0. They don't make it undefined. They make the function equal 0. So at these critical numbers, our slope is 0. So therefore, these are either telling us where we have maxes or mins. Okay, so creating that number line, if these are my intervals, then left of -3 would be -infinity up to -3. Then my next step would be -3 to -1, and then from -1 to positive infinity. Picking a test number in here like -4, plugging it in here, I would get a negative value. -4 in here would give me a negative value. So this is y prime. Right? These two things right here are y prime. Now, why did I not include a 3? Why did I not make one of these lines a 3? All you ever need in a sign chart is something that has the potential to maybe be positive or negative. If I had a 3 written here instead, 3 is forever 3. This line is just going to be occupied by a bunch of plus signs. So it's kind of wasting my time. There are optional things that don't have to be here. If it were a -3, that could affect the product of everything that's going to be in this column. So a -3, if this were a -3, you bet I'd give it its own line. Positives, or anything that will always be positive, you can actually omit. So right now, up to here, this is showing where y prime comes from. It came from this times a 3. So a negative times a negative became a positive. So the slope of the graph is positive. So what's the behavior of that graph? It's heading up. It's increasing. So this graph, when it's left of -3, and notice we always use round brackets. We don't want to get ourselves caught to be at a certain location, because at a certain location, maybe my slopes are 0 or undefined. So we have round brackets. Something in between here like a -2. -2 in here is negative. -2 in here makes that positive. So this times this, because this times this gives y prime, I'm now negative. So what is the graph doing between here and here? It's falling down, or it is decreasing. And then something to the right of -1, like a 0. A 0 in here makes a positive. A 0 here makes a positive. So the graph slope is positive, so it is increasing. If you have a look, you've actually almost drawn the graph. If you picture, this is telling you what the graph is doing. You can see something happened right here. What is right here? When you transitioned at -3. So the graph, first of all, does exist at -3. -3 was not a denominator here or an NPV. So the fact that I went from increasing to decreasing, I have a max at x equals -3. That's the first derivative test right here. Positive slope, negative slope. That's the first derivative test. Down here, from decreasing to increasing, what must be happening right here, which really is telling you you're at -1, you have a minimum at x equals -1. So you have found the x values. If somebody wanted you to find the y values, you would take these x values, sub them in here to get the y values. But they're asking, where does the local max occur? If I want to give the point, okay, I will put -3 back in here, work it out, I will get a 0. Oh, sorry, I've skipped a step here. Well, number 3 from our list was find the extrema. So that was doing it right here. So this was step 3. And my minimum is going to be when x is -1. And if I subbed a -1 back in here to save time, that would be a -4. Could I draw the graph after all of this? Yes, you could. If you took all this information over here, my x-intercepts are 0 and -3. I have no asymptotes. After I'm done here, I'm going to be heading up. Now we know at -3 I have a max. And from this equation, I see that my graph for Math 30 is going to bounce off the axis at -3. It is an odd function. So one arm heads up and one arm heads down. So you should always start drawing from the right. You would kind of get this idea of what's happening there at this graph. So if you have a look at taking all this information, what you knew from Math 30, all this information that at -3 you had a max, somewhere over here at, I just kind of estimated, so I'm a little bit off, but that would be my minimum. So I could have started with a point there and a point here at -4 and drawn it more accurately. But that's eventually where you will get to, is being able to, from this chart and all other information, draw your graph. Okay, something not so familiar. So this one right here. If we were to change how it looks and write it as a power, we would have this. So nothing is off limits actually to put in here for x, because no matter what I take, I'm going to be squaring it, but then I'm being asked for a cube root. So even had this been negative, a negative value inside, I can still find the cube root of a negative. So this graph has no NPVs. It goes on forever and ever. Okay. What I do know, looking at this and just thinking about the math of it, this will never be negative. There's, no matter, even if I started with x is -4 right now, when I square it, it's going to turn positive. If I start with 0 and squaring it, this thing will never ever have a negative value. So this thing will always either be positive or 0. That's the actual function. So it's going to be on the x-axis or above the x-axis. If I want to find x-intercepts, I would make my y 0, so that's a 0. To find a y-intercept, I make my x 0, so that's a 0. Asymptotes, no vertical ones because there's no denominator. No horizontal ones because the top is a higher degree, right, than the bottom, so I have none here. If I go through and find my y prime, so that's bringing my 2/3 down, and then taking 1 away from the numerator, I'll have -1/3. So this could be written as 2/3 cube root of x. So that is your formula for the derivative. So now I'm going to set it equal to 0. All right, we're going to find the critical numbers. So I have a 2 on the top, I have a 3 cube root x on the bottom. So on the top, nothing will ever make the top 0, but on the bottom, if x were to equal 0, that would be undefined. So there is a critical number. There's no solutions from the numerator, but you look everywhere. So we do have a critical number from the denominator being 0. Okay, so the idea is there is no slope at 0. Does the graph exist at 0? Sure, we can throw a 0 in there. So the graph exists at 0, but we can't find the slope there. How can you not find a slope somewhere? You have a corner, you have a cusp, you have a vertical tangent. So something weird is going on at 0, okay? So you would go to your sign chart because 0 is your critical number. That's where you get your intervals from. So my first interval would be left of 0, so -infinity to 0, and positive infinity. So do I need a 2 in this chart? No, 2 will always be 2. Do I need a 3 occupying a line here? No, but I do need cube root of x. So if I were to take a negative number like -1 and put it in here, the result would be negative. A positive number put in here would be positive. And that's it. That's the whole thing that made up y prime. So there's nothing here but one negative, so the slope is negative left of 0. This is positive, so the slope to the right of 0 is positive. So what is the behavior of y? Y is decreasing. Here, because the slope is decreasing, right, heading down. Here it's positive. 0, why was that a special point? Now remember, the graph does exist here, but something else is going on here. I can't find the slope here. So, but it did go from down to up. That is a minimum. That is absolutely a minimum. So I have a local minimum, down here, at x equals 0. Because the graph does exist there. So we have a local minimum, and that's happening at 0. So if I want to know the y value of that point, I could put a 0 back in the original equation. So at the origin, I've got a local minimum. My graph was decreasing on the left of it, but increasing on the right of it. So if I take a minute and think about this, could, let's see, how about if I drew this first? Say, okay, here's what I think that original graph looked like, right? This is a minimum. Yes, it is. To the left, my graph was decreasing. To the right, my graph was increasing. But why is this not right? Well, if this were the graph, would I have said my slope here is undefined? No, I would have said my slope is 0. So what do I do different so that everybody knows there was a problem here with slope? There we go, the cusp idea. Now, definitely the slope is not 0. Now I would say my slope is undefined. So you got to kind of think. You have everything it takes to make that graph, but you have to look for a little bit extra information. Okay, next page. All right, so this one you should be able to picture for Math 30. So there is our cubic function. So we already know what it looks like. If I get the derivative, I would have 3x squared. So I set the y prime equal to 0 for 3x squared. So if I divide both sides by 3, I get 0. So what does x have to be? X has to be 0. So immediately go to my sign chart. So this starts moving very quickly now. So if that's the only critical number, it created the intervals negative infinity to 0 and 0 to positive infinity. I don't need the 3 here. And you know what? I don't even need the x squared here. 3 would always be positive. X squared will always be positive. But I typically will put anything here that involved an x. But really, this was optional. We can tell this first derivative is always going to be positive. So the slope is always positive. This graph is always climbing. And you should be able to picture a cubic graph, right? There you go. That's what this graph would look like. But there's the math that supports everything now. So you can tell the slope forever is positive and it matches here. So putting a negative number in here is positive. Putting a positive number in here is positive. That's everything that it took to make y prime. So the slope is always positive there, and the slope is always positive here. So the behavior of y, it's always climbing, and then it's always climbing. So hold on, if a graph is climbing and then climbing, I can't connect these now. They don't go. This is not a max right here. This 0 value, it's not a max, it's not a min. How did you climb? Stop for a minute and climb. Very briefly right here, so I didn't exaggerate it enough, but right here in this case, because I can see it, the slope would have been 0. So climbing, brief stop, climbing, it's not a max or a min. It would be a POI. It would be a point of inflection, which change is where a graph changes from, in this case, concave down to concave up. So there is no extrema. There are no maxes or mins. There's just a POI. So that would be the answer for number 4. Again, is that there's no extrema. Okay, this probably doesn't look familiar. You're not used to this one here. So if I went through and found all this other information, I could get this. Now, finding the first derivative, it will be 1/3 x to the negative 2/3. Writing that as a power is kind of more revealing. I would have this. So if you have a look at this, here you go again. It's always going to be positive or undefined. Okay, so slope here, if no matter what I'm putting in here for x, I'm squaring it. So therefore, this value is always positive. So if I go back here and put all the same values in, I'm never going to make the top 0, but I could make the bottom 0, and that would come from x equals 0. Okay. So there's the critical number here is x equals 0. Putting it back in here doesn't give me a slope of 0. It gives me a slope that's undefined. All right. So does the graph exist at 0? There's the graph. Does it exist at 0? Yep. Does the slope exist at 0? No, it doesn't. So looking here, then we see if this represents slope, then for anything except 0, the slope will always be positive. So there's no extrema. If you haven't hit it, right? If you do not change from positive to negative slope or vice versa, you never have a max. So I've done this for you, shown you your graph. The graph definitely does exist at 0. How come the slope doesn't? Because the tangent, slope of the tangent there would be undefined. Okay, we have Fermat's theorem. If a function has a max or a min at c, then the slope there will be 0 or the slope will be undefined. Now you can't turn that around though. So if we have a max, there's a max, then the slope could be 0. Or maybe here's a max, the slope could be undefined. And I could do the same for minimums. But you can't change that sentence around and think it's still true. If you know your slope is 0 or your slope is undefined, could you now say that you now have a max or a min? Nope. I can draw something where the slope is 0 that isn't a max or a min. How about that? Right there. That is not a max or a min, but my slope for sure is 0. So taking this sentence and reversing it doesn't give you a true statement. But this is true, okay? If you know you have a max or a min, then you are guaranteed the slope there is 0 or undefined. Okay, so there's just some examples here that have been done for you to have a look at. From start to finish, what your thinking should be, how you would go through all this thinking. So I'm showing you here, by the way, when I found my formula for first derivative. You look everywhere. Is there a critical number from the top? Yes, it's 0. Is there a critical number from the bottom? Yes, positive or negative 1. So making x 0 gives you a slope of 0. Making x positive or negative 1 gives you an undefined slope. And that in this case does go back to the original function. The original function does not even exist at positive or negative 1. But the fact that I now have these 3 critical numbers, I can make my sign chart. So I've shown you putting in this factor here. This one right here, that's optional. It's always going to be positive, so I really didn't need to waste my time. This negative 4 could have had its own line, so if I had wanted to, instead here, give a negative 4 its own line and just constantly said that's negative, give an x its own line and said how it's going to be changing, then that would be fine. But if you want to put them together and think about what the results would be, you can do that as well. So taking a negative number for x and putting it in here, a negative times a negative was a positive. So you can read through that one and have a look. Again, right now the graphs are optional, but it gives you a reference graph to look at after all the math that you did. Something like this, do not keep things as 2 separate terms. Try and combine them. So giving them common denominators, you get something much more useful. So from this one, it would be very easy actually. I'd use this one to find the first derivative, but I would use this form of it to answer the Math 30 characteristics. So again, going through this, getting your critical numbers, making your chart, deciding what was necessary or optional. And then always watch for little hints. If I had come up with this as a formula for y prime, have a look at it. It's never going to be negative, ever, ever, ever. The slope of whatever graph this came from is never heading down. It could be 0 if the top was 0. Because of my domain. But this will never ever result in a negative value. So whatever this thing looked like, it was always heading up or maybe leveled off at 0 for a minute. Or if this was, again, the formula for slope, it's always going to be negative. This will always be positive, okay? Always be positive. If I put a 0 in here, the slope could be 0, or a positive number in here, the slope will be negative. So whatever graph this came from, this formula now tells me the graph always heads down or maybe does have a 0 value. One last topic here. So this bottom example you can read through later on your own. This is really important. This idea of a closed interval. So we're now not talking about a graph that goes on forever and ever. It starts at A and it ends at B. So example here, there's no arrows. So it is like I have cut this thing off, okay? You are guaranteed if you have a graph that has definite start and ends to it, somewhere is going to be an absolute maximum and somewhere there's going to be an absolute minimum, okay, on that interval, if it's continuous. There's a rare case where you might have had a horizontal line. Now, where are you going to find the maximums and minimums? Well, they could have been at a critical number, for sure. So you would still want to go through your work, find the first derivative, solve it for equaling 0, and find your critical numbers. Or it could have been at an end point. All right, so if we had taken a graph, okay, so right now we know this thing, if it goes on forever, has no absolute max or min. But if I cut it off right here and I told you just look right here, well, all of a sudden it does. It does have an absolute maximum value, and whatever height this point was would be that maximum value. And it does have a minimum value because I cut things off and kind of looked at it that way. So there's your procedure. If you are told, so you're going to watch for these square brackets, in a specific snapshot, where is this thing the highest or lowest it's ever going to be? It might be at a critical number, but it might not. You do not need to bother with a sign chart. This is straight math. You're looking for big numbers and small numbers. So you will still factor your formula and find a critical number. So you now will find the points that belong to those critical numbers. So you'll take the x values, sub it into the original equation, and you'll know those points. If you know the points, you'll know which one of those two are higher y values, okay? But then the ends, maybe the ends come into play now. Maybe the way the graph was cut off at that end, you have a max or a min there. So you will take the x values of each endpoint to find their y values. So now you're going to compare all these y values. You'll find the highest and the lowest. So we did this on page 3. You were given this function. So if all somebody asked me to do was find the max or the mins, not draw the graph, the max and the mins, but on an interval, that -4 and that 1 become very, very important. That's where the picture started and that's where the picture ended. So you still find the first derivative, you still find your critical numbers. So you take this -1 and you find the y value that corresponds to it. So that tells you the graph has the point -1, -4. The other critical number was -3. So you take -3 and you put it back in there and you have this. So you know something's happening at these points. This one is lower than this one. But how about the ends? How about -4? So if you put a -4 in here and you find the y value, that tells you the point is -4, -4. Oh, these are the same height, aren't they? This point and this point are both have heights of -4. The other endpoint was a 1. If I put a 1 back in here and work it out, I get 18. So now it's up to you. Find the highest and the lowest. So out of -4, 0, 18, and -4, that's my max. That's the highest point. So when x is 1, that becomes the absolute maximum of this snapshot of a graph in that interval. Then what's lowest out of these? Oh, there's 2. These are both -1. So these would share the name of being the absolute minimums. So I drew the graph here, but I stopped it, right? This is like you taking a picture of a graph. Well, what is the absolute highest? Right there. What is the absolute lowest? There's 2 of them. Okay, so an extra interesting one for you to have a look at and go through and read. That's a lot of information there. You're probably going to want to go back, read through this again. And the purpose of this lesson was for finding the highest point on a graph or the lowest point on a graph. Sign charts are priceless. They will help you. There are shortcuts as we go through things. You'll see there's shortcuts, but a sign chart will never fail you. To get the sign chart working, you have to be able to factor your first derivative. And you're looking everywhere in that first derivative, numerators and denominators, to get your critical numbers. That makes your sign chart. And then again, it's always the bottom of your sign chart. Like when I look at this, increasing to decreasing, and the graph does exist here. That's got to be a max. Decreasing to increasing, and the graph exists at a 1. How do I know it exists at a -1 and a 1? Because I could go back and look at the original equation. And then right here, decreasing to decreasing, geez, that looks like a POI. But I need more knowledge than that. 0 on this graph is impossible. I can't put a 0 here on the original graph. So there is no graph at 0 because that would be an indication, hey, heading down and then heading down again, that's not a max or a min. That's usually a POI. If the graph had existed at 0, this would have been a POI. But the graph just doesn't even exist there. So there actually is the picture of the graph. There's a vertical asymptote here. So lots and lots of information. So you've got work to do in your textbook. Watch the video a few more times. Probably good to have a printed out copy. So that's it. Calculus is so much fun.